it's my honor to be the coordinator for the next session. We will have two speakers in the session. The first speaker is Dr. Furong. He is a chair professor of chemical and biological engineering at Hong Kong University of Science and Technology, so HKUST, and he also served as HKUST as the founding director of Center for Polymer Processing and Systems since 2007, and International Molding Communities as the president, Society of Advanced Molding Technology since 2017. And Dr. Gao has a long bio list, and I couldn't have enough time to complete it, so I'll give time to Dr. Gao.
Thank you, Professor Li. It's really a pleasure to be back in Hangzhou. In Hangzhou, I have quite a few friends, and my talk today is talk about a little bit about process control or process system engineering, and in conjunction with polymer processing. And for those audience who attend the control conference, possibly you have heard my talk before. But today I see quite a few new friends here, so it's for you. So my talk here is essentially a condensed version of my talk at the dialogues some time ago. So we sorry you could hear me twice, right? Okay, chemical process have been increasingly, become diversified. So batch become a resilient process. That's why we need to do some work on batch process. Depending on time, I may skip some slides. So this is my outline of presentation. First, I'll talk about what is injection molding. And through this process, we hopefully to illustrate some batch natures. And then the batch nature call for PSE, specifically developed for batch process, because continuous method may not work perfectly for batch process. And we'll talk about control, monitoring, modeling, and a little bit about sensing. Then after that, we try, we have, based on those knowledge we developed sort of commercialization project. And then I talk about what we are doing currently and we conclude. And this should be very quick. Most people in PSE areas are chemical engineers. So I have these slides here mostly for control people. And the chemical process can be divided into continuous and batch, two types. Batch have its own natures. One of the important natures, the process activity goes through an ordered set of activities. And also, more importantly, this process repeats itself. And I also doing injection molding polymer processing, and this may not sound very familiar for you. The process basically converts plastic into various products widely used for medical, transportation, and electronic industries. And you see old photo of my lab, and this is the typical injection molding machine. And some of you may see this before. What we do, we take off the control system, then we develop the control system by ourselves. And the process is fairly simple. The process goes through several phases. In other words, ordered process activity goes through the so-called injection, packing, and cooling, and several processes, and then the process repeats. And I'm not going to go to details about each phase, what do we do, okay? And then we consider this as a batch process or semi-batch process. Then if I abstract the process a little bit, then we have some, I have a cartoon here. The process basically goes through several phases. Within each phase, you have different concerns, or each different phases have different impact to the final qualities. And then the process repeat. You can imagine when the manufacturing requirements have been met, then the process would be changed to make another product. And I have to apologize, we have some Chinese characters here. The Chinese characters are important that summarize the batch process natures. And the first 4 characters says the same process is being used to make different type of products. It's the one nature. The second nature, when you manufacture the same product, the more of the same product is being manufactured by repeating the process. The third phrase here explains within each batch the process divided into several phases. The last statement says within each phase your control objective or your concern varies. And in English, I did not manage to produce the same equally. You can see the beauty of the Chinese language. Each different thing, we have 4 characters. And the Chinese like to write hidden messages. So if we take the first character of these 4 phrases, it literally means multi-time variations. So multi-time variations is essentially a key characteristic of batch process because the batch process characteristic changes within traditional time, changes within the batch time, changes with product time. So the multi-time variation is the key phrases I coined first. So this batch process, different from continuous process, is also facing certain challenges. Because for batch product, you change product quite frequently. Once you change product, the process condition changes. Those change of process condition leading to significant changes of process characteristics. Therefore, those characteristic changes leading to the control or automation system changes. Right? And you can imagine the product changes leading to a significant changes of those characteristics. Therefore, you need this automation system have wide range of adaptiveness. Okay? This is one challenge. The second challenge is when you change the product, you have to, you need to switch to production immediately. You cannot wait for too long. So you need to have this adaptiveness to be ready very quickly. So the batch process facing these 2 challenges. And also the process have certain requirement. The requirement is in the contradiction with the characteristic. Earlier I talked about this, 4 characteristics. And those 4 characteristics are essentially multi-time variation characteristics. You also have certain requirement. Basically, you need to make the operation to be ready almost instantaneously. You need high precision and safe operation and good quality. Those requirements and those characteristics require certain challenges for PSE community for batch process. Namely, when the product changes, the modeling, everything changes. So the complexity in the modeling, both you need the instantaneous model requirement without a big contradiction. This is one. In terms of control, we can do precision control under certain operating conditions. But it's very difficult to have precision control over a wide range of conditions. So therefore, you have large operating ranges versus control performance consistency part contribution. And also for monitoring, because each phase characteristics is different, how do you analyze the process while accommodating these multi-phase natures? The last, not least, we are batch process. Ultimately, we're making a product. Products have direct requirements. Well, those direct requirements are so-called qualities. Unfortunately, those qualities cannot be directly measured. All we can do, we can make certain process variable, repeatable, in hope that quality is repeatable. So therefore, we have so-called quality indirect estimation versus direct quality certification challenges. So our PSE research on batch process is in hand to address those issues, address modeling issue, control issue, monitoring issue, and quality issues. So our group at HKST, based on multi-time variation natures, how do we systematically develop modeling, control, monitoring, and quality control system for this type of process? I call this process automation systems. It consists of the following a few components. One is the modeling, which serves the foundation for everything. Two is the control, to make sure it's the means to make the repeatable quality product. And the monitoring and analysis is the safety and the efficiency assurance. Ultimately, the quality is our goal. So that's the four elements consist of so-called batch process automation systems. We try to address issues, how do we develop efficient modeling strategy after product switches? And also, how do we accurately control the process with large dynamic ranges? How do we do real-time monitoring and analysis to suit batch process multi-phase natures? And how do we ensure quality? And by the way, quality may be multi-dimensional, sometimes contradictory. How do we ensure those qualities? Because of the time, I may not be able to report all those findings, but I do quickly scan of the philosophy we have for those four areas. Now let's go back to injection molding very quickly. And injection molding, the quality are determined by how well you control for each injection phases. So specifically, the quality are determining how well you control for those four phases. But because of time, it's not possible for us to go over all this. I illustrate to you the control of velocity. And what's the basic nature? Why do we need to develop batch process method? So injection molding, actually, I'm doing this work since my graduate students' days. It's over 30 years. We have gone through several different phases for process control. Broadly speaking, we can divide the phases into four phases. The first phase, actually, as a fresh graduate student, I have no idea what's the difference between batch process and the continuous process. By the way, my first degree was in automation, not chemical engineers. I'm a fake chemical engineer in chemical engineering department. So what we do, we directly apply the process control methods, which are mostly developed for continuous process to batch process. You can imagine we're facing certain challenges. And then we realized we invest heavily in the equipment, in the sensor actuator, we still cannot achieve perfect, very good control. Then we realize batch processes have unique characteristics. Then what we do, we modify the continuous process control method to suit those characteristics. That's our second phase of process control research. After that, then we realize for batch process, there's one big advantage we can take because process repeats itself. If we do not do great job for first trial, we can do better. Therefore, what do? We introduce iterative learning to batch processes. And iterative learning actually is widely used in the robotics industry. Robotics is very good. It's very repeatable. Chemical process, you can understand. It's so difficult to precisely describe it. It's repeatable, but it's not so good repeatable. So what do? We develop our own method we call two-time dimensional control. We coined this thing. Because depending on time, I go very quickly. Otherwise, I know it's our exit time. Right? You demand 5 minutes only?
6.
Okay. Anyway, because of the time, so I skip all those details. Okay. We've gone through this all generation of different control. Okay. And because I summarized into different phases, that's the second phase. That's the third phase. Then we use a chip actuator, and then we can combine the classical feedback control together with integrated learning control. Then there's a series of academic challenges surfaces. How do we develop this two type of control? How do we make sure these two types of control are not in conflict with each other? Okay, so I skipped all those mathematics. I skip all those mathematics. Then eventually, what do? We can describe a batch process as a two-time dimensional system. And obviously, everybody understands time is one-dimensional, never go back, right? So for batch process, we can describe this as two-time dimension. One is the traditional time, and one batch, two batch, three batch, the case batch, it's repeating itself. Then if we describe the batch process as two-time dimension, one is traditional time, T, another batch dimension, K, then we describe this thing as two-time dimensional dynamics. With this, it's possible for us to use information happened in the past. That's no problem, right? And also, the beauty of two-time dimensional things, you can predict, you can use information of future, of past batches. Basically, you know what's going to happen in the future. With these fundamentals, you can develop very effective control strategy, okay, to control the batch process very well. And here is using the two-dimensional control strategy we developed. You can see we use a very cheap valve, and we can control the velocity so perfect after certain cycles. You can see the first batch, we have nothing to know. We have very lousy actuator. The performance for the first batch is very lousy. Then, with the batch through batch, control performance becomes almost perfect. So that's the batch process control work report. Then I'll quickly talk about the other three areas. And for the theoretical analysis, the good thing is I noticed Professor Jin Lu will be next speaker. She did those work while she was at HKLT, so I leave that to her to save time. Okay. For process monitoring, for continuous process, we know we collect data, change see how they change with time. We result in a big two-dimensional data structure. For the batch process, we do this for each batch and result in something called 3D structures. Our good friend of John McGregor at McMaster, his main contribution was to turn this 3D data matrix into 2D so that we can apply those statistics. Then we realized there's a big problem here. If you turn this 3D data into 2D, all these phase natures lost. Because different phase operation contributing to final quality different, we lost that information. We realized this phenomenon about 15, 20 years ago. So we developed so-called phase-based batch process monitoring. With that, we can analyze how each phase's operation affect final quality. And then with the final quality, we can go back to see which phases you need to enhance the control, make it more repeatable, more precise. Of course, with time going on, we realize the batch process can switch from one phase to another phase, not in a big jump. You have transition. We realize this transition has more important contribution to final quality evaluation. So we incorporate transition phases. After that, now the big data is very hot. So now we have data. So this thing here, whether phase or not, you see essentially we chunk the process data into different blocks. We can use multi-block data to analyze that. Okay? So with that, we're capable to predict which phase contribute to your quality important. With that, we're also being able to calculate which variable contribute to quality important. Okay? I realize by chairman we have 2-3 minutes left. I talk about another important thing. For batch process, I'm manufacturing one product, let's say 1 million pieces of the same product. I accumulate a huge sum of data. I can develop data-driven model easily. However, the next product I develop to be molded, to be manufactured, I have no data. How do I use the abundant data I collected for last product? Okay? We use the concept so-called model migration. This concept we developed almost 20 years ago. It's in competing with my computer science colleague. He developed so-called transfer learning. It's become very hot. Unfortunately, I'm chemical engineers. We developed our method. It's not as hot as transfer learning. But the concept is that for original process, original product, I have abundant data. I can develop a model. And for new product, new process, I have few data. But we realize these two processes are similar in terms of characteristics and lots of things. Then our philosophy, can we migrate the model you developed for this process quickly and efficiently for the new process? We call this model migration. And this concept actually is in discussion with our colleagues of Zhejiang University, Professor Zhao. He coined model migration. So with this philosophy, we can develop numerous different methods. Okay? So we have model migration. I see the chairman urged me to conclude, and and the same we do for the batch process. Basically, traditional continuous approach, we work on one time dimension. Then for the control, we treat batch process a 2-time dimensional dynamic process. With the model migration, we introduce 1-time dimension, product time dimension. Basically, we have transformed in batch process automation from 1 time to 2 time to 3 time. Thanks to Luis, we published paper on the JPC on these concepts. And I speak this, even though this work is originated by Chen Xi, the chair, while he was at HKST. And this thing here, we intend to shift process control based on process variable to ultimate final quality. Because the sensor we develop to a certain degree can reflect the product qualities. With that, we have developed the thing a little bit more systematically. And in the modeling, we developed, based on process similarity, we developed so-called model migration strategy or philosophy or paradigm. For control, we define batch process as two-time dimensional dynamic process. We develop 2D control so that control performance can enhance along both time direction and batch direction. For monitoring, we recognize multi-phase nature. We develop process based on different phases to analyze, to monitor. And for quality, because of time, I will not go into details. And also, what we do based on this philosophy, the methodology we developed, we have developed a control system and a sensor system to be promoted, to be applied for polymer injection molding industry. Right now, we have maybe about 1,000 site installation using the strategy we developed. So, Professor Lee, I skip this. Okay? I skip what I will do, and I don't think I need to conclude. Thank you very much for listening. I'll stop here.
Okay.